Another way of figuring out how the carbon cycle works is to look at the various reservoirs, and one way is to look at the oceans. It turns out the nuclear tests of the 60s have been very useful in doing this. This is a profile in the Atlantic, radiological profile in the Atlantic of the injection of tritium into the ocean. Basically excess tritium, so from the nuclear tests, and you can see that at equatorial latitudes it doesn't diffuse down very far, get into the ocean very much. Where you have bottom water formation in the North Atlantic, you do get some rather deep injection. These measurements were made in 1972 and 3. The next view graph shows how it's changed. And there was a major measurement program in 1981, and they haven't, I don't think, redone the plots, but these are sort of the changes that have occurred. There's not much change in the lower latitudes, where water is basically, deep water is coming up and rising to the surface. But in the North Atlantic regions, where the surface water is sinking to the bottom, there have been deeper penetration of tritium. That gives one a reading of how fast the tracers can move into the ocean, and basically how fast carbon dioxide can move into the ocean. Well, if you put these fluxes all into a sort of a summary estimate, and here we go back to this number of gigatons per year. Fossil fuel emissions, the best estimates are sort of 5.2 gigatons. The biospheric reservoir, there's a large range of estimates about what's happening. And it depends on whether people believe you're cutting down the tropical forests at rates that occur in some regions, or whether you're getting regrowth of forests in, for example, the northeastern region, which was cut down early in the century and is regrowing tremendously. So there's quite a range of estimates here. This is probably the best estimate. The oceanic estimate is reasonably well understood because of these radioisotope measurements, and the atmospheric increase is pretty well understood. Well, the rate of increase per year in the atmosphere is pretty well measured. Now, if you try and add these up and see if you're in balance, well, if you add up the ocean and the atmospheric increase and equate them to fossil fuel, you're in good shape if the biosphere is doing nothing right now. But if you go out and talk to ecologists and people studying the forests and the tropics, most of them believe that there has to be a source here. If that's true, then we really don't understand this cycle quite well enough. But it's reasonably close, so it's within maybe 20% or so of understanding what's happening. Well, the question then is what's going to happen in the future, and so people go out and make projections of future energy use, and the next view graph shows one of them. They're rather incredible numbers, to my way of thinking. A lot of this information comes from the United Nations. And there's a great sense that that information has a lot of political information behind it. That is, developing countries want to grow at 5% per year rather than have the capability of growing at 5% per year. So 5% per year gets built in. But if you look at per capita use, you see little change in North America. There's certainly some conservation, I guess, and growth will tend to balance out. But a lot of growth in some of the developing countries. And this is sort of a 50-year forecast where they're projecting 6 times as much energy, for example, in the developing parts of Asia. Whether there's the economic and social infrastructure to accomplish that is not at all clear, but those are the kinds of projections that exist. As you can see, basically global per capita use doubles and global population doubles, so that the total amount of energy use quadruples, and most of it will probably come from fossil fuel, although certainly there are other alternatives. One question that's come up a great deal is whether going to synfuels is good or bad. And just for reference, I can show you synfuels with respect to other things. The reason synfuels are more expensive in terms of the amount of carbon they put out is because it takes energy to produce them. And so that's basically included in this estimate. So this is really per 100 quads of useful energy out. They've actually used a good deal of energy to create the synfuels. But if you make calculations, any reasonable sort of U.S. program in synfuels isn't going to have much impact in terms of the global numbers that are considered. But I think the argument on the other side that is used by environmental groups is basically it's a symbolic issue. If the United States is going to start talking in the future about a CO2 problem and yet is using the most, using energy in a way that produces by far, well, produces more carbon than it really has to, it's symbolically a bad thing to do. Well, so as a result, one makes projections about when CO2 is going to double. Estimates made in the early 70s with this historic growth rate of 4% per year led to a doubling early in the next century. If you don't change fossil fuel rate, and if you keep a constant fossil fuel emissions here, basically after some time here, you don't have you don't double until way out in the 22nd century, I guess. I guess the current estimates sort of are looking toward a doubling late in the next century. That doesn't mean there aren't any problems till late in the next century in terms of climate, or aren't any issues, or aren't any effects, but that's just sort of a convenient number that people look at. Well, one might ask a question, is there anything we can do about it technologically to keep the CO2 from increasing? And it turns out, I guess most people's feelings are there's very little that one can do. Removing CO2 at the point of emission is just an extremely expensive process. Energy-wise, it takes one power plant to remove most of the CO2 from another power plant. And so it's not something you're going to do. Basically what you do, for example, if you take coal into a power plant, you're taking one carbon atom in. If you're going to create a calcium carbonate to take out, you're taking not only that carbon atom, but a calcium atom and 3 oxygen atoms out in your train. So it becomes very expensive and energy-wise, and just a tremendous amount of material. There is some thought about sort of injecting this material into the deep ocean, but gathering it is just inordinately expensive. Growing trees has been suggested. In fact, there's a sort of one of these, congressman is going to solve the problem by putting trees all along our interstate highways. I think you can get a feeling for that in terms of the seasonal change, how many trees that would really involve. It's just not something that's going to be accomplished. Once CO2 is in the atmosphere, it's kind of dilute. Again, you can talk about trees, although you run into other problems of nutrients and other kinds of things. There has been talk about fertilizing the ocean, bring your oil tankers over and then running backwards with phosphorus or phosphates and stuff to put them in the ocean. I think unlikely. Certainly switching to other fuels or reducing CO2 fossil fuel emissions helps. Biomass will help, certainly, because that's basically taking carbon out of the atmosphere, and so it doesn't add to the net total. And if you can use nuclear or solar or some way to make hydrocarbons from atmospheric CO2 or energy from the atmospheric CO2, you help. But it's it's not likely to be a problem that you're going to be able to prevent, or an event you predict. Well, to summarize basically the carbon cycle aspects of it, this was a point made, as I say, 25 years ago, that we're doing something that hasn't been done before. CO2 has probably been very high in past geologic times, but certainly not in past historic times. And so we're really doing a giant experiment, and the question is, what is the outcome going to be? The basic system that it will affect is the climate. And what I'll be talking about next is the climate system and some aspects about it. And first I ought to perhaps define my terms and what I mean. Climate is basically a measure of the probabilistic state of the atmosphere and the moments and the means and things. Where weather is a momentary kind of state of the system, I guess one of the little euphemisms or phrases about it is that climate is what you expect and weather is what you get, which puts it reasonably well. It's not a quantity. Climate isn't really very well defined, and in the National Climate Act, the Congress decided it wouldn't even try and define climate. It just used the word. Certainly, as we change the climate, the weather is going to change. But really what we're interested in terms of how we live in our lifestyle is what the climate is, what the means are going to be in the moments and the changes in the frequency of climatic systems. Well, a climate system is an extremely complicated, involved system. This is just sort of one drawing of it, and I'll show maybe some others in a moment, that has a lot of things affecting it that one has to treat. Usually what's considered internal to the system is the atmosphere and the oceans, but with CO2 being such a long-term problem, you start having to worry about the ice and the state of what's happening on the land. But there are a lot of different things that can change and influence what's going to happen. Climates of the past have changed, and one of the, well, yeah, the next slide shows some of the factors that people have thought have influenced some of these longer changes. And there's certainly more. This is just sort of a list. But variation, this is a time scale across the bottom with a year being here and 1,000,000 years out here. But there's certainly a lot of things that can change. The composition of the atmosphere is what we're most interested in terms of CO2. But ice can change, positions of continents can change, just all kinds of things can have effects. And so if you look at information on the past climate system, you can see that the climate has actually changed. And this sort of goes back, increasing in order of magnitude each time in years. But the recent climate was sort of warm, this is northern hemisphere basically, was warm in the 40s, kind of cold in the latter part of the last century, and has been cool recently, and I'll come back to an update of some of this information later. In terms of the last 1,000 years, however, we've been in a relatively warm period. There was what was called the Little Ice Age. Now this information, a lot of it comes sort of from Europe, and it may be biased by Europe, or there's some question about whether it's a global phenomenon perhaps. But it was kind of cool several hundred years ago, and then during the Viking period it was almost as warm as it is at present.